Okay, so hello everyone, Happy New Year and welcome to the first COFFIES Seminar of 2024. Today we will have a special arranged seminar in alignment with the Heliophysics Big Year's January theme, The Sun Touches Everything. We will have 3 speakers from all 3 NASA Drive centers, each giving a talk about the sun's impact from different scopes. Our first speaker will be from COFFIES, Dr. Shea Hess-Webber. Dr. Shea Hess-Webber is a research scientist at Stanford University and team lead of COFFIES Center Effectiveness Team. Her research interests focus on bridging the physics gap between solar subsurface acoustic perturbations with observable surface features, with particular interest in coronal holes. Today, she will talk about how the sun touches everything. So today we will go from the sun to farther away space. So then the next speaker, the second speaker, is Professor Amy from CGS. Professor Amy Keesee is an associate professor in University of New Hampshire, and she is the CGS lead of Broadening Impact team. Her research includes 3 areas: magnetospheric physics, instrument development, and laboratory plasma physics. She uses satellite data to understand the dynamics of the magnetosphere during geomagnetic storms. Any problem? Okay. And today, Professor Amy Keesee will give a review about dynamics in Earth's magnetotail during geomagnetic storms. And our last speaker will be Erick Powell from Boston University. Erick Powell is a PhD student in the astronomy department at Boston University. His study is focused on MHD simulations of the heliosphere, and he has also a lot of outreach experiences. And he is part of the SHIELD NASA Drive Center. Today, his talk will be about our habitable astrosphere. So thank you for all of the speakers and all of the people. I will now give the Zoom to the first speaker today, Shea.
Hello, everybody. Let me just share my screen. All right, and slideshow view. Can you all see and hear me? Okay. Hopefully.
Yep, we can hear you.
Okay. I was going to say, hearing nobody say anything, that means that, yes, everything is fine.
I'm not seeing. Is this my fault?
Is it better? Should I just carry on? Tim, you know how to find me. I can give you this presentation.
It's like zoomed in for me. I mean,
oh, weird.
It doesn't look like that for anybody else. Okay, carry on.
Okay. All right. So, hi. I think most of you know me at this point. I am Shea Hess-Webber. I am one of the leads of the COFFIES effectiveness team, and I also am a helioseismologist by trade. But one of the things that I'm really interested in, as Riju said, I don't remember telling her this, so I'm very honored that you remembered. I'm really interested in connecting the solar interior and the solar exterior. And so that fits well into COFFIES because all of the interior dynamics influence what happens on the outside and arguably vice versa, right? So that's why I'm here. What I want to talk to you all about today is how the sun touches everything. As Riju mentioned, this is part of the Heliophysics Big Year. So just to, oh, there we go. Just to give y'all a little bit more insight on what the Heliophysics Big Year is, since we're doing this in conjunction with it. It's a NASA initiative where essentially what we're trying to do is bring the solar physics, the heliophysics community out to the public and make it, like, celebrate it with the public, but also bring the public into our science and like let them get hands-on with it. So my talk today is going to be a little bit more of a lower level talk, because hopefully then members of the public will be able to tune in and understand and enjoy all of the ways in which the sun touches everything. So just a heads up for next year, or not next year, next month, the theme of the month, there's a theme every month of the big year. The theme next month is Heliofashion, which I'm particularly excited about. I don't know if you can tell, but I wear the sun on my sleeves. So stay tuned for that. We're going to have some cool stuff going on next month as well. So without further ado, I'm going to get started. First thing I wanted to talk about, starting small scale, is how the sun touches me personally. I don't know if you can see through the Zoom screen, but I am of the sort of person who turns very red very quickly when I'm out in the sun. Thankfully, my job entails sitting inside to study it. So I thought I'd talk a little bit about how I get to go out and enjoy the sun, which is by wearing sunscreen. So what causes sunburn are the ultraviolet rays that manage to make it through Earth's atmosphere and hit our skin here on the surface of the Earth. There are different kinds of ultraviolet light. Essentially, those kinds are binned into how much energy they have. The highest energy are the ones that really give you sunburn, but you can still have skin damage from the lower energy UVA wavelengths. So in order to protect against all of those wavelengths, you want something called broad spectrum. You may have seen this on your sunscreen bottles before. This really means that it's covering both the low energy and higher energy UV radiation that's coming through the atmosphere. You also probably want something around SPF 30. Anything lower than that isn't going to really protect you as well for as long. And anything higher than that is kind of overkill and isn't actually going to protect you any more than an SPF 30 would. So if you kind of see this plot here that I shamelessly stole from some amazing sources online, you can see it's not a linear trend. So as you get to about SPF 30, the protection is about the same. Okay. And then also sunscreen. So the sun makes us wear sunscreen, and the sunscreen can affect the environment. So this is another way sort of that the sun propagates its effects into the environment. Sunscreen often has chemicals that are bad for the environment. For example, they can create coral reef whitening. So essentially that's just coral reef die-off. Even if you're not at the beach and you go outside with sunscreen on, when you go back home and you shower and rinse all of those chemicals off, they make their way into our water. So it's really important to be choosing sunscreen that is reef safe. Generally what this means is instead of chemicals, they're using minerals instead in order to protect our skin. And there's some information here. I'm not going to talk a whole lot about it, but if anyone's interested, I'm happy to share these slides. You can have access to the papers and resources, and also be able to see a little bit more about what to avoid in your sunscreen if you are able to use environmentally friendly sunscreen. So that's how the sun touches me and how I get the sun to be nice to me a little bit more. Next, I wanted to talk a little bit about how the sun touches Earth. I think that you'll hear more about this when Amy talks next. So most of y'all probably heard about space weather. Space weather is essentially any sort of activity coming from the sun and its impacts on Earth. So if you've heard of things like solar flares, coronal mass ejections, the solar wind, all of that can come and impact us here on Earth. And then it can disrupt things in a number of ways. Generally, as human beings on the surface of Earth, we are generally well protected by the Earth's magnetic field and the Earth's atmosphere. But it can affect, for example, astronauts out in space. I have sort of a little NASA, it looks like a picture, actually. It's very well done, but a NASA drawing here depicting people on the moon. We have the Artemis mission coming up. They need to be concerned about space weather because they are outside of Earth's protection when they're on the moon. Same thing if we send people to Mars, they're going to have to be careful about space weather coming and impacting Mars. It affects our technology a lot. It can down satellites because it heats up the Earth's atmosphere and expands it out so that there's increased drag or frictional forces that pulls those satellites down. It can create shorts within satellites. So a lot of times they want predictions of these solar storms in order to power down the satellites to prevent shorting from happening. It can create currents on the ground that can degrade pipelines and short out circuitry on the ground, create blackouts all over the Earth. And it can do some really awesome things like create the beautiful aurorae as well. And, you know, so a little bit of good, a little bit of bad, a lot of beautiful. Yeah, that's how the sun touches Earth. Again, I think you'll hear more about this when Amy's talking. So kind of expanding out further from Earth, how the sun touches not Earth within the solar system. Again, you may hear more about this later when Erick is talking, but I just wanted to give a couple of fun facts about, you know, how the sun touches other planets, other things in our solar system. I am old enough to count Pluto as a planet still. So we're going to talk a little bit about Pluto. From Pluto, the sun is about 1/900th of the brightness as it is here. It's brighter than our full moon is. What I read in preparing for this is that there is a point when during sunrise or sunset when the sun is about as bright as it would be at noon on Pluto. So, you know, you can kind of use that to gauge the brightness if you were standing on Pluto. In terms of how long it takes light radiation to reach other planets, it takes about 8 minutes to get to us here. Mars, it would take about 13 minutes, and at Jupiter would take about 43 minutes. And I wanted to highlight, we know that solar radiation is impacting other planets because we can see aurorae on those other planets. So I've got some pictures of Saturn here and Saturn's aurorae, Jupiter's aurorae. And then in the middle here actually is Mars. These are relatively recent results. We didn't necessarily know that Mars could, well, I didn't at least know that Mars could have aurorae because it has such a faint atmosphere and you really need particles in the atmosphere for the solar radiation to interact with to get aurorae. But Mars does in fact have aurorae, and it actually has it all over the planet because Mars's magnetic field is not just dipolar, it's really small scale all over the place. So you can actually get aurorae all over the planet, which I think is pretty cool. Things outside of our solar system. So I don't know if SHIELD thinks about these sorts of things, maybe, but instead of a heliocentric point of view, we can think of other-centered or allocentric. So we can think about what the sun would look like from planets around other stars, from exoplanets. So just for example, our closest star is Alpha Centauri. It's about 4 light years away. The sun's magnitude from a planet around Alpha Centauri would be about as bright as Alpha Centauri is to us here on Earth. So somewhat equivalent, which is kind of cool. So just look at Alpha Centauri and that's about what we would see. There's some really interesting articles online that kind of show depictions of about how bright, so the diameter here isn't how big the star would look like, but how bright the star looks. So from Alpha Centauri, you know, kind of a scale of brightness in terms of what like the stars in Cassiopeia, for example, would look like. For those of you who don't know about apparent magnitude, I kind of put a plot on here for you to gauge the difference. The lower the number, so into the negatives, the brighter the object is. And then the larger the number, as you get into the positives, that's more faint. So this 0.5 is right around here where we see a lot of stars and we can perceive stars. What I read is that approximately the distance away that you can approximately see the sun as a star as you go further out is around about 50 light years. I think Pollux is somewhere in the 40s, and it's a pretty faint star from Pollux. So yeah, I just thought that was kind of an interesting inverse view of how the sun touches things even outside of our solar system. So now I want to talk a little bit more about specifically what I do, and you know, how we as solar physicists, solar astronomers, know and see that the sun is touching everything in our heliosphere. So we know from both in situ measurement, so like if you have a detector sitting on a satellite that's out in space, and it can measure that there's plasma flowing by it and magnetic field going by it. So we know that things are coming from the sun. Also remote observations, which essentially you can think of as pictures. We can see that there are things coming off of the sun as well. So we know that the sun has a constant stream of particles. We call it the solar wind. The sun is rotating, so that wind is also rotating in what we lovingly call the Parker spiral. It's an Archimedean spiral, but Eugene Parker, is the first person to have suggested that this is what's happening with the solar wind coming off the sun. You can kind of see an example here. Here's some images in different wavelengths of the sun. So some coronal images, so outer atmosphere, chromospheric images, which is inner atmosphere, and then the magnetic field on the surface. Hopefully it's coming through on the screen, but you can also see these white lines that are coming out and back in. That is a modeled representation of the magnetic field going from positive to negative magnetic field regions on the sun. And then you can also see in this model over here, this is called the WSA-Enlil model, and it's a very good physics-informed, data assimilated model of what we think the solar wind is doing at any given time based on all of this input data that we get from observations, and the physics that we understand of the solar wind from in situ data. So you can actually see this was from January, actually, yeah, just a day or two ago. So you can see there's an eruption happening here. These are density plots. If you want to play around with this, when I share the slides later, you can go to this source button, and there's a whole like dashboard that you can play with in terms of like looking at space weather models. It's actually really fun. But so one thing that you can kind of see from the model is this is a top-down view, obviously. We don't have satellites up there, so we can't see this top-down view. So we need something like a model in order to be able to understand what's happening. But like I said, this model is data assimilated. So really, this data on the left here is some of what goes into the model on the right. But one thing maybe you haven't thought about in these pictures is that this is just one side of the sun, right? When we take pictures from Earth, we're only seeing one side of the sun at a time. The sun rotates, so we do see things coming around, but at any given point of time, we can't see the far side of the sun. We don't know what it's doing. We don't know if there's new magnetic flux materializing. And that is really important when you're trying to create a full 3D model of the sun and the solar wind. Okay, so just kind of to show you an example of this. So if you take this magnetic field plot down here at the bottom right, and stretch it out so that if you think about like the Earth as a circle, but we can stretch that out onto a 2D map, that's kind of what we're doing here. So we're seeing magnetic flux in the red and the blue, polarized. And this is actually old data back from 2014. So we know from a rotation around that this new active region, this new region of magnetic flux appeared on the far side because it rotated around and we could then see it. But it was there before we could see it. So what does that do to the global magnetic field, which is really important for things like predicting the solar wind. So the bottom plots here are basically if you project out the magnetic field out into like close to the sun, but away from the sun, this is sort of what the connectivity of the magnetic field looks like. And you can see if you zoom in on these areas that are surrounded by dotted lines, the structure within those regions actually changes. You have a new feature here, things kind of move around a little bit, and then you can actually use observations to say, okay, it looks more correct compared to observations when we include this magnetic field region on the far side. So by knowing what's happening on the far side of the sun, we can actually make better predictions and inform the models more correctly. We can see the far side of the sun by using acoustics. So I'm not going to get into a lot of the physics of this. I mentioned I'm a helioseismologist, that is what we do in order to see the far side of the sun. You can think of it sort of like sonar or echolocation. We're using sound waves to probe the sun. So on the left here, this is what we see on the sun, the magnetic field of the near side of the sun. And we have observations that are well correlated to that in EUV wavelengths. So again, those wavelengths that could potentially hurt our skin, they are also useful scientifically. But we actually have a few years limited data of that same wavelength on the far side of the sun. And so we can then use that to compare to our acoustic or sound wave representation of the far side of the sun and see that we do pick up some of these active regions on the far side. So we can use that to understand some of the magnetic field structures and features that are happening on the far side of the sun. This is bigger than I thought it was going to be, but so this is putting some of those acoustic maps together with the magnetic field. So this is actually a full 360-degree picture of the sun, and you can see as it rotates, some things come around to the front that I believe if you look at this region here, you'll be able to see this go from near side. We detect it on the far side again. Okay, so and then here it comes around. So we can actually really use this data of the far side to inform how things are then going to impact everything else in the heliosphere. And just really quickly, we can actually convert these acoustic maps into a magnetic flux signal using machine learning, which then allows us to take those far side acoustic signals, these near side observations, remote sensing observations, and put all of that into this model to make our forecasting and our solar wind models more accurate. And I think that's all that I have. So I will stop there. I maybe am a little bit over in time. So I don't know if there's time for questions, but feel free to reach out to me. Feel free to ask me questions later. Feel free to ask me questions in the chat. And yeah, I'll stop sharing.
Sorry, I didn't notice I'm muted. Maybe we can have time for one quick question before heading to the to second speaker. Any questions? Okay, maybe for time's sake, we will move to our next talk, Professor Amy Keesee.
All right, let's get this going. All right, are we in the correct mode?
Yeah.
Great. All right, so thank you for inviting me to talk. I'm Amy Keesee. I'm at the Center for Geospace Storms, and I'm located at University of New Hampshire. But Shea gave a very nice introduction, so thanks, Shea, about space weather and how the sun really impacts us here at Earth. And CGS is really trying to study that and make models that are potentially predictive for some of those space weather things that could happen, so that we understand better what's going on, what causes some of those phenomena that are both beautiful or could be potentially detrimental to us. So I am specifically going to talk about the dynamics in the magnetotail. That is one of the critical components of what happens within geospace and during these storms. So the sun touches everything, and like we have already seen, the sun drives these geomagnetic storms that happen at Earth. So we're going to start with these artistic renditions of what we're looking at. So this is obviously not to scale, but we have our sun, And Earth is basically sitting within the atmosphere of the sun. So this is Earth here, and Earth initially has basically a dipolar magnetic field. So when you guys played with bar magnets and you did the dipolar field, that's what it would normally look like. But because the sun is always sending out the solar wind, it is going to squish what we call the day side of the magnetic field, and then it stretches out the night side into this long magnetotail. So it's this side, or the night side, the magnetotail, is what we're going to be focusing on today. So lots of cool stuff is happening. So here is NASA's movie. Again, artist rendition of what's going on. So the sun is going to eject a coronal mass ejection, and it's going to come and it's going to hit the magnetosphere. It results in a geomagnetic storm that, as you can see, has a lot of magnetic reconnection. Now, reconnection happens both at the day side as well as here in the magnetotail. And it's all this stuff that's happening, especially as a result of that magnetic reconnection in the tail, that really drives a lot of the interesting stuff that happens during these storms. Now, one thing I want to point out, especially for the solar physicists, is that not only do coronal mass ejections cause storms, but also co-rotating interaction regions can drive storms in the magnetosphere as well. Co-rotating interaction regions are coming from coronal holes where you have really high speed solar wind coming out, and that high speed tends to overcome the slow solar wind behind it, and that interaction can create a storm at Earth, and it's co-rotating with the sun, and so we often see storms every 27 days occurring with that co-rotation of the sun. So they actually end up being slightly different styles of storms, so it's interesting to compare what happens between the two. So that's definitely something where the sun is touching us here at Earth and driving those different types of storms. I will say, in terms of space weather, they're kind of different as well. So the coronal mass ejection type storms tend to be stronger and have quick impacts, whereas the co-rotating interaction region type storms tend to be not as strong, but last a little bit longer, and so have a little bit different impacts in that way. Okay, so moving on from those artist renditions, this is actually a simulation using the model that we are building as part of the CGS Drive Center. So this is a visualization from a storm. If you guys heard not too long ago, there was a storm where SpaceX had launched a set of their Starlink satellites, and a storm was happening at the time, and they lost a whole bunch of them to satellite drag. So the thermosphere density went up, and those Starlinks didn't make it. And so this is a simulation of that storm that happened. So like I said, we're going to be focusing on the magnetotail. So these lines that you can see here, these colored lines, are magnetic field lines. And there's a lot of stuff going on here on the night side and the tail. And it's a little bit hard to see, but you can see some magnetic reconnection happening. And when the reconnection happens in the tail, it's kind of like a rubber band that's getting pulled and then releasing like a slingshot, and it's going to accelerate particles towards Earth. So that's the kind of stuff that we are trying to study, is those particles getting accelerated towards Earth and what happens with them. Okay. All right, so now we're looking again at our simulation here, and now you're looking down at the Earth, so sort of on top of the North Pole, and the sun is to the right, so you can see this sort of compressed day side and stretched out magnetotail, like we were talking about before. And what we're really trying to understand is, again, like I said, you have reconnection and that slingshots particles towards the Earth, and you can see from the simulation that you have these regions where those particles are going to come in, and it kind of happens in these localized spaces at different places across the tail. And as those particles come in earthward, the ions tend to move around one direction, whereas the electrons go the other direction around the Earth, and they're going to rotate around the equatorial plane, and they create what we call the ring current. And the ring current is what we use to describe how strong the storm is. So the ring current is measured by the deflection of Earth's magnetic field around the equatorial plane using ground magnetometers. And we measure that with an index called the DST, or Disturbance Storm Time Index. And so this is an example from back in 2003, when we had big storms around Halloween. This is the measurement of that DST index. And so typically, since it's a change from the background Earth's magnetic field, it's typically sort of around 0. But then when it gets deflected, we measure how strong that deflection is. It goes negative, and we look at different ranges to say how strong the storm is. So we can say sort of a moderate is anything beyond 50 nanotesla. Intense is beyond 100 nanotesla. And then superstorms are beyond 250. So the Halloween storms were definitely in that range. So that's something we really look at to understand. So understanding how strong a storm is going to be really depends on how these particles are getting injected from the magnetotail into that ring current region. All right, so how do we study these? How have we known about them? And a lot of what we've done, of course, is looking at satellite data. Now, unlike the sun, the magnetosphere does not send photons our way. So we can't image it and just take pictures of it like we can with the sun. So we have to send up these satellites that take all these localized measurements. And we've learned a lot. So just 3 of the more recent missions are the Van Allen probes, Themis, and magnetospheric multiscale. And these are multi-satellite missions that give us localized measurements. But because space is so big and we're taking these localized measurements, it's really hard to tell what is going on everywhere across the magnetotail. And one of the big questions is, how important is these injections, so these localized injections of particles going to the buildup of the ring current versus just general convection? So the particles also sort of move just in general towards Earth. And it's a big open question to understand the different contributions of those 2 types of motion. So satellite data has helped some, but definitely has been some limitations in understanding that. So the model that is being built as part of CGS is called the Multiscale Atmosphere Geospace Environment Model, or MAGE. And it has a bunch of different components, understanding all the different parts of geospace. And they're all tied together to really help us understand what is going on. So lots of different parts of this model to look at different regions, and then all coupled together. So here again is another look at that simulation. Again, looking down and really trying to understand what happens with these particles as they get injected towards the inner magnetosphere. And one of the critical things that was shown in work by Sarathi et al. Is that the resolution of the model itself is really important to get those physical processes correct in the simulation. So a lower resolution, these are particles, and whether they actually made it close in enough to the Earth to be trapped in the ring current. And this is a higher resolution one, showing that you really need that high resolution to get those particles in there to be show physically accurate simulation of the ring current. Okay, so we've been using the simulation to really understand this question about the injections versus convection, and how much buildup of the ring current happens. So this is work by Ciola et al. Looking at that. So if you sort of take this view that we were looking at, where you're looking down on Earth and you have the magnetotail, and you sort of, again, this is like Shea was talking about, where you take your curved image and you flatten it out onto a map. This is sort of a similar thing where you're taking this side and you're flattening it out across space here, and then as a function of time over here. And we're looking at enthalpy flux here, and where you see this really intensify is where you're seeing this flux of particles in towards Earth. And if you also, so again, this is the flux quantified here in this plot, and then this orange is the ring current. So you can see that the flux increases at the same time as the ring current is intensified. So definitely these injections are playing a big role, and this can all be quantified to show that this energy transport is really having one of the biggest sources of the ring current buildup. So since we can see that it is really localized in all these different places across the magnetotail, we also want to look at where does that happen? Does that tend to happen more in one place than other across the magnetotail? So this is another study that came out by Sarathi et al., really looking at sort of the different distributions of where these are happening. And again, we're looking down on the North Pole. This one's a little bit tilted, so the sun is sort of to the right, but down a little bit. And when we're looking from the North Pole down, we talk about, like I said, this is the day side and this is the night side. We also talk about dusk being towards up in this image and dawn being down. And so that helps us sort of get a spatial location of things. And looking at this particular storm that was simulated, there was a lot of differences about what was happening towards dusk. And you can see that there's stuff happening towards dusk in the simulation in the tail, and then also in the aurora simulated here towards dusk. But then there are also some features happening at dawn, and it kind of was very latitudinal dependent. And so the data there was matching up well with what was going on in the simulation to understand what was happening and where, and really helped explain some of the current structure that happens due to the changes in the magnetic field during these storms, which gets really complicated. And in this storm, there is definitely a dawn side occurrence of some of these regions and injections that are happening in the tail, and that's showing some more dawn side perturbations of the magnetic fields seen on the ground as well. So that really helps you to understand when we're talking about if you can have power blackouts, where those magnetic field perturbations are going to happen. Localized is really important to understand. So looking again at that same simulation, this is a picture where you can see maybe a little bit better all that stuff happening towards the dawn. And one of the things that we compared to was using a technique that I use called energetic neutral atom imaging, which gives us a way to sort of image where the ions are across the magnetotail. So again, looking down on Earth and seeing into the tail, you're seeing these regions of ions that are towards the dawn side. And so we wanted to know a little bit more about this occurrence. So when are things happening towards dusk versus when are things happening towards dawn? And we actually looked at our entire database of storms from the TWINS energetic neutral atom images. And if we look at all of it, there's a lot more happening at dusk in general. But if we break it down by year, it seems to change where they're happening across dawn versus dusk. And this is really quite interesting because there's been a lot of statistical studies using the satellite measurements that seem to say most things are happening towards dusk. So I was actually part of an ISI team that was looking at dawn-dusk asymmetries across our whole solar system. And particularly in the magnetotail, there were so many things that happen much more at dusk. And this is just one example where using Themis measurements and seeing a lot of these particle injections, and it definitely happened more towards dusk. So it's really interesting to see this occurrence that sometimes it seems to be happening more at dawn. So this is an open question that we're hoping to address more as we go on. So my key takeaways is that the sun touches us here at Earth by driving these geomagnetic storms. There are different types of storms depending on the storm driver coming from the solar wind, and particularly the coronal mass ejections versus the co-rotating interaction regions really drive different dynamics during the storms. The magnetotail is a really critical part of what happens during a storm because a lot of the energy from the sun gets dumped there, and reconnection injects those particles towards the Earth and really leads to the buildup of the ring current, how we define the strength of a storm. So the critical part of CGS is that we're using this MAGE model, and we're using their simulations to show these critical contributions of the flow regions in the tail and how that leads to ring current buildup. And then we also have a lot of open questions, and I just gave the one example of the dawn versus dusk location of these things, and we're using the simulations combined with data to try to address some of these open questions. Thanks.
Thank you, Amy. Questions? I see one in the chat. Shea, do you want to ask the question?
Sure. I was just wondering if, Amy, the CGS models, like the high resolution models, are those full MHD?
So let me go back. There we go. Okay, so this component, Gamera, is MHD, and then it's coupled to a bunch of other parts. So the ring current itself is not an MHD code. And then there's other parts like go to the ionosphere and lower stuff that are also not MHD. So it's the more global part that does the Magnetotail is MHD, but then it's coupled with a bunch of non-MHD codes.
Awesome, thanks.
Any more question? Alex?
I have something a little bit related. So in the simulation GIF that you were showing, there's a lot of large vortices in the kind of like outer shell. Do we actually see that in situ? Do we really expect those vortices to be that kind of like
Are you talking about here?
Yeah, like there, and more so on the top, it seems to be even more pronounced. Like you'll see like some really significant vortices.
So my understanding, and I am not the modeler here, is that some of this is the Kelvin-Helmholtz stuff that can happen towards the edge, and that is realistic.
Okay, thank you. So if no more question right now, we can move forward to our last talk. Erick?
Awesome. Yeah, let me share my screen real quick. Okay. And can you see my screen?
Yeah, title page beautifully.
Wonderful. All right. Well, thank you for the opportunity to talk today. I'm Erick Powell. I am joining you guys from Boston University, where I'm a PhD candidate and a member of the Shield Drive Science Center. And just like everyone else, I was asked to give a talk with the topic of the sun touches everything. And today we already heard some great talks from the other drive centers, and those talks mostly focused in how I interpret it as the sun as a threat to us in some way or another. The sun actively driving something at Earth that affects us. And I want to look at this in a different way. I'm going to be looking at the sun as a shield, how it protects us. And so if we jump right in. Okay, so we're going to start with a very zoomed in, very simplified model of the Sun-Earth system. We have the sun at the center, Earth magnetosphere slightly off, and a really low resolution of the heliosphere, which you will see. We zoom out very far. I'm going to be talking about the global shape of the heliosphere, a very large scale structure. If you think of the distance between the Earth and the sun of 1 astronomical unit, in the global heliosphere, we are talking about distances of a minimum 150 AU towards the closest part, towards interstellar space, and then a very long extended tail. This is the canonical view of the heliosphere, of this giant comet-like heliosphere, where the tail, similar to the Magnetotail, extends off in the opposite direction for a very large distance. But just to orient everyone about what I'm going to be talking about with the heliosphere, sun, as we heard, emits solar wind at a very high speed, and that solar wind leaves the surface of the sun and shoots radially outward for many, many astronomical units until it encounters the termination shock, where it goes from a supersonic flow to a subsonic flow. So it goes from very fast to much slower, and it heats up in the region we know as the heliosheath. And eventually, if you continue along this path, you will cross a boundary known as the heliopause, which separates heliospheric plasma from interstellar plasma. And inside the heliopause is what we know as the heliosphere. And this is a bubble carved out in interstellar space by the sun. So, if you were to look outward from Earth towards other stars nearby, you can actually see analogs of the heliosphere. You end up seeing what are known as astrospheres, which is the same concept, but instead of the solar wind, think of a stellar wind leaving from each of these stars, shooting out radially and interacting with the interstellar space that they are in. So some stars, we have evidence, we can see a heated bow shock in front of them that gives us some sort of an idea that there are other heliospheres, astrospheres in this case, around other stars. However, for the heliosphere, this is the only astrosphere that we know is habitable, mostly because we're here. So we know that the environment that the sun carves out for us is protective enough. The environment's right for life because we made it. When we're looking at exoplanets, we don't know exactly what their environment is like. And even if they may have the right temperature, they may not actually be able to be the home to life because maybe their environment isn't conducive to that. So if you were to look at all the nearby stars in our local environment, here's a diagram, an artistic rendition of where we are in our local interstellar environment. We have the sun at the middle. It's traveling off in this direction of the yellow arrow. And we have relative directions and distances to nearby stars. So for example, here's Alpha Centauri. Here's some other stars where we actually know we've been able to observe astrospheres around. And then, so these symbols right here, that's an astrosphere around a star. And if you see these little planets, these are stars that have exoplanets detected. And while there is a case where we see astrosphere and a planet, it's not exclusive. You don't know if they have both. But we do know that our astrosphere plays an important role in habitability. Because if we zoom out here, in the heliosphere, we have taken measurements of cosmic ray flux. And as Voyager left our solar system, we saw that Voyager, hold on, let me minimize. Okay. We saw that from Voyager, we saw that the heliosphere actually shields about 70% of the cosmic rays that would be in the interstellar medium. So the heliosphere does shield us from approximately 70% of cosmic rays that if the heliosphere wasn't there, the Earth and the magnetosphere would actually have to deal with. These are cosmic rays up to 1 GeV. There is higher energy cosmic rays, but for these purposes, there is a large chunk of dangerous cosmic rays that the heliosphere actually sheds or shields us from. And these cosmic rays, if you're able to look closely at the Voyager observations here, these cosmic rays go up and down, and they actually they vary along with the solar cycle. So as the sun increases in activity and decreases with activity over time, we actually also see that the cosmic ray intensity follows this in an inverse fashion. So not only is it a static shielding, it changes over time. And it's something that is very important for, in particular, space travel. This was touched on a little bit earlier, that, for example, if we are planning for an astronaut to travel to, say, Mars or the moon, you actually have to consider their radiation environment, because if you have too much cosmic ray flux on you, it is equivalent to a radiation dose. and NASA cares about their astronauts and want them to be safe. So if you look here, a 500-day trip to Mars would actually be about an order of magnitude higher than the maximum radiation that we allow workers to have. So if we are going to consider longer time for space travel, say the Artemis missions or even further than that, we have to understand our local environment and what our astronauts would expect. But the thing is, to know how our cosmic ray environment is, we actually have to understand how cosmic rays move through the heliosphere. And what I'm showing on the right is just a couple trajectories from a work that tracked cosmic rays in the heliosphere. And it may look like a bunch of squiggles, but what this is a cosmic ray entering the heliosphere and bouncing around all the way into 1 AU where the Earth is. And one thing that is not well known is exactly where these cosmic rays enter the heliosphere. If, for example, they come head on, enter through the nose, or if they actually have an easier way getting through, say, the tail. And that is one of the main thrusts that we want to understand in the SHIELD collaboration. We want to have this digital twin of the heliosphere through our modeling that would allow us to predict, say, the radiation environment in a time-dependent fashion. Say, if we leave during solar minimum versus solar maximum, how would the cosmic ray environment actually be filtered? How would it change over time? And that's a long-standing goal that we hope to get through this collaboration. But now I am going to slightly transition and briefly talk to you about how I fit in with this collaboration. So you may wonder, how do we even know this about anything about the heliosphere? And it was briefly mentioned about in situ observations for the magnetosphere. For the heliosphere, we are also limited in how we can actually figure stuff out. One of the ways that we have information about the heliosphere is Voyagers 1 and 2. These are spacecraft that allow us to have in situ observations. However, there's only 2 of them, and they went at a certain time. They only sample very specific points in space. So we are very limited in what we can pull out of those instruments. However, there's another way to probe the heliosphere and astrospheres, which is with Hubble Space Telescope, and specifically Lyman alpha. And this is where my research comes in. I work with the MHD models in our group, and I've actually been comparing to Lyman alpha. So Lyman alpha is a transition, it's a transition of light. And when stars emit at Lyman alpha, that radiation travels through interstellar space. It encounters an astrosphere, the interstellar medium, and finally enters the heliosphere and is observed by Hubble Space Telescope. And what's really convenient about this setup is you end up with an observation where the heliospheric effect and the astrospheric effect are separated. So when you look at the observations from Hubble Space Telescope, you can actually tell what your heliosphere does to what is going on with your heliosphere and what's going on with an astrosphere. So what my work has been doing is looking at nearby stars and looking and probing the heliosphere, what the neutral hydrogen environment is like. So here I'm just throwing a part of my work out there where here's our heliosphere model. And this gray line is the direction towards the star that we're looking at. And I'm simulating what we would see if we look that way and can compare it to observations. So I've been able to do that with a couple different directions. Alpha Cen is one of the target stars that we actually know has an astrosphere. And we were able to probe different directions through the heliosphere and have a way to probe the neutral hydrogen environment in our heliosphere. And if we understand our heliosphere, we will be able to apply this to astrospheres, and hopefully in some of the upcoming research from SHIELD, we'll be able to understand our local environment a little bit more. Thank you. If you have any questions about my work or SHIELD, please email me at ianpowell@bu.edu. We also are doing a lot of outreach with our group. So if anyone is hoping to do any eclipse viewing, I would appreciate contacts with me because we ran an event for the last partial eclipse and I think it went well. But I think if anyone else has any ideas, we'd love to team up. Thank you.
Thank you, Eric. Questions? We have we are about 1 hour time anyway. We may have time for one quick question before we close for today's seminar. Okay, so if no questions, we will. Any follow-up questions? People can contact speakers or contact me. Oh, Sushan has actually raised hand. Okay, so we will give the chance of last question to Sushan.
Eric, really nice talk. I loved some of the infographics you showed. Just wanted to ask about the dosage graph that you showed for like 500 days on Mars and 180 days during transit. That is regardless of cosmic rays that are filtered by the heliopause, right? So that graphic was just showing difference between how much the Earth's atmosphere filters out?
So yeah, so on that image, there were different cases. There is a comparison if you are at sea level because the magnetosphere also filters it out. So that was assuming you were outside, you were doing this travel.
All right, thank you.
Okay, so let's thanks to all our speakers today, and thank you for all attendee of the seminar to attend this wonderful talk time. And again, we will have our seminar monthly, so hope to see you guys all next month. Bye.
Thank you.
Thank you. Bye-bye.